Special topics: queuing, simulation, and decision analysis. In this unit, we consider three special topics. We start with queuing, or the study of waiting lines. We will look at queuing theory, design, and characteristics. Next, we will look at business simulation, including appropriate application, advantages, and disadvantages. Then we will consider the Monte Carlo simulation and walk through an example. Our last topic is decision analysis. We will look at business decision-making processes, including the use of decision trees, risk, and expected monetary value. Queuing theory is the study of waiting lines and applies to both manufacturing and services. Here are some situations where waiting in line is common. The table lists the situation, who or what is in line, and the associated service process. One that I think is interesting is the example of the computer system. Computers, especially those with single processors, only do one thing at a time. Since multiple programs may be running at the same time, they must wait in line and take their turn to be executed. Can you think of an example when you have waited in line that is not on the list? This process diagram further defines the three parts of the waiting line. In this case, a car wash waiting line starts with the arrival of dirty cars. The number and time distribution of arrivals must be analyzed to understand customer demand. Next, the service system includes the queue and the service facility or car wash. The design of the queue will be based upon demand characteristics, the service process, and available space. Finally, customers exit the system by driving away in their clean cars. To analyze customer demand using a Poisson distribution, this equation is used. P of x is the probability of a certain number of arrivals, x, which is the number of arrivals per unit of time. Lambda is the average arrival rate, and e is the base of the natural logarithm. Don't be intimidated by this equation. If you have access to Microsoft Excel, use the Poisson.dist function to simplify your work. Here are two examples of a Poisson distribution for x values from 0 to 10, given lambda values of 2 and 4. For the first graph, the peak of the distribution is near 2, while the peak is near 4 for the second graph. The equation is repeated here. Queuing designs are concerned with the number of servers and number of phases. The number of servers reflects how many service stations are available in parallel. The number of phases counts the number of steps required in the service process. For example, if a bank has a single line feeding multiple windows, that would be a multiple server, single phase queuing system. Additionally, the service is defined by the amount of time required to deliver the service. At an automated car wash, the times are constant, while service at a bank may vary based on the type of customer transaction requested. These flow diagrams show different queuing system designs. A dentist's office with only one dentist would be a single server, single phase system. At this McDonald's, the service process has two steps, or phases. The first window takes your order, while the second window gives you your food. This would be a single server, multi-phase system. At this bank, we have a single line feeding multiple teller windows. Each teller can perform all services, so there are no additional steps required. This would be a multi-server, single-phase system. This process flow shows a multi-server, multi-phase system for a common college recruiting process. There is a single queue feeding two parallel sets of processes, or phases. Special topics: simulation. A simulation is a mathematical model of a real-world system. Simulations are used to study the system's properties so as to help managers make fact-based decisions regarding the real system. Here we see examples of some applications of simulations. Note that simulation is used instead of costly decisions that may not be accurate. For example, the construction of a major production facility is an expensive and risky investment. The simulation can be used to verify the design rather than having to rework the building when issues arise. Scheduling decisions can be modeled in advance, rather than making the errors that might affect employees and impact customer service. To make use of a simulation, you start by defining the problem to be analyzed. Next, we define the variables associated with the problem. These variables form the foundation of a numerical model of the problem. Different scenarios are identified. For each scenario, the appropriate variable values are defined and run within the simulation. The results are analyzed with the goal of selecting the best alternative as the basis for future action. Simulations have many advantages. Simulations can model complex business situations, including complications and what-if scenarios. A short simulation run can model years in simulation time. Existing operations are not affected by simulation runs. There is no impact to your current operation. Disadvantages include the development time for the simulation model and program. You may get different results given the same inputs. Creation of the various scenarios to be tested must be thorough and fully anticipate future conditions. Finally, each model is unique. Monte Carlo simulation is used when future states cannot be fully defined. In this case, we set up probability distributions for important variables. For each variable, we define an interval of random numbers. Based on these ranges, we generate random numbers which are used in the simulation runs. Let's use Monte Carlo simulation to analyze demand at Barry's Auto Tire. We start by collecting demand data over the last 200 days. We see that on 10 different days, no tires were sold. Next, we see that on 20 days, 1 tire was sold, and so on down the list. This is the frequency. Next, in the third column, we divide the frequency by the number of days, 200, to get the probability of occurrence for each level of demand. Notice that the probabilities add up to 1. Finally, in the fourth column, we calculate the cumulative probability by taking the probability and adding it to the cumulative probability above. For example, for a demand of 5 tires, we have the probability of 0.15 or 15% added to 0.85 to get 1 or 100%. Next, we assign random numbers to the data. We copy the data, demand, probability, and cumulative probability from the previous table. Next, the intervals of random numbers are defined based upon the cumulative probabilities. For the first cumulative probability of 0.05, we define the interval of random numbers as 0,1 through 0,5, with the top number matching the cumulative probability multiplied by 100. For the next demand level, we start with the next number up, 0,6, and go to the next cumulative probability of 0.15 for a range of 0,6 to 15. We continue until all demand levels are completed. Our next step is to select numbers from a table of 2-digit random numbers. Here's an example of such a table. We start at the upper left and select the numbers going down the first column, 52, 37, 82, etc. On this slide, we're going to simulate 10 days of future demand. From the table of random numbers, we add the column of random numbers, 52, 37, 82, to the second column. Looking at the random number, we map the value to the intervals of random numbers taken from the previous table. A segment of that table is shown to the right. For example, for day 1, the random number is 52. This value falls within the range of 36 through 65, so the simulated daily demand is 3. For day 7, the demand is 2, since the random number 33 falls within the range of 16 through 35. We continue the same process down the list. Summing the daily demand, we get a total of 39 tires over 10 days for an average of 3.9 tires. Here we see the impact of the Monte Carlo simulation. The expected demand works out to the sum of the demand multiplied by its probability. The result is an expected demand of 2.95 tires. Note that the Monte Carlo simulation came up with a daily demand of 3.96 tires. You can improve your understanding by rerunning this example yourself by using the second column of random numbers in your calculations. What result did you get? I'll give you a hint. It should be 2.5 tires per day. Special topics: decision analysis. Decision analysis is used by operations managers to use data to make key decisions. We start by defining the problem and the factors that influence the outcome. We develop measurable objectives and a model. We evaluate each alternative using the model and select the alternative with the best outcome. Finally, we implement the selected alternative and verify the results. In decision making, a discrete course of action that may be chosen is known as an alternative. The state of nature is the status of the situation at some point in the process. In this method of decision making, a decision tree is created and used for the analysis. The symbols used in the decision tree are shown here. The rectangles represent decision modes from which alternatives branch out. The oval represents a particular state of nature. Here's an example of a decision tree. The decision node on the left represents the decision as to whether to construct a new plant facility, and if so, what size will the plant be. We see three alternatives that result in three different outcomes or states of nature. Next, we consider each state of nature with two alternatives, favorable and unfavorable markets. Now we gather the data necessary to make the decision. The three alternative paths are listed on the left, with the value given favorable and unfavorable markets. For example, if we build a small plant and markets are unfavorable, we will lose $20,000 versus doing nothing. The previous analysis assumes we have a clear understanding of the future states of nature. But in reality, uncertainty exists. Different outcomes or states of nature may occur, each with its own probability. We can use different methods to complete the analysis in an uncertain world. The most optimistic outcome is the maximax. This is the maximum outcome for every alternative or the highest possible gain. The most pessimistic outcome is the maximin. This is the lowest outcome for every alternative or the least possible loss. For the equally likely value, we find the alternative with the highest average outcome, assuming that each state of nature is equally likely to occur. Now let's apply these concepts to our building decision. We start by identifying the maximum and minimum in each row to populate the fourth and fifth columns. We then calculate the row average and add that value to the sixth column. So for the alternative of constructing a small plant, the maximum between $100,000 and the negative $20,000 is $100,000, while the minimum is a negative $20,000 and the average of the two numbers is $40,000. Selecting the maxi-max, we get $200,000 for the first alternative. Selecting the mini-max, we get $0 for the do-nothing alternative. Finally, we find that the equally likely value is $40,000 for the small plant alternative. You've now seen the worst case and best case alternatives. Based upon this analysis, what alternative would you choose? Another decision analysis method uses expected monetary value. We start by estimating the probability of each possible state of nature. We assume that the states of nature are mutually exclusive. Each alternative is independent of the others. The probabilities add up to 1. We choose the alternative based upon the expected monetary value, or EMV, for each. For each alternative, we multiply the payoff of each possible state of nature by its probability. Summing these products, we get the earned monetary value, or EMV, of that alternative. For our example, We have estimated the probability of a favorable market at 60% and the probability of an unfavorable market at 40%. We now calculate the EMV for the three alternatives. Substituting the values from the previous table, we see that the second alternative, building a small plant, is the best option. The EMV method provides a clearer decision. Key points to remember. In this unit, we reviewed three special topics. We start with queuing, or the study of waiting lines. The end-to-end view includes the arrival of customers, waiting in line once in the facility, participating in the process, and then leaving. The Poisson distribution can be used to predict the pattern of customer arrivals to better estimate demand. The lines and services provided can be laid out a variety of ways. We might have single server or multiple servers. The number of servers might be the number of teller windows at the bank. The service process may have multiple phases. The phases are the steps required to deliver the service. Business simulation supports the decision-making process by creating a mathematical model of a real-world situation. The model may be executed manually or through the use of a computer. The advantages of simulations include the ability to create fairly complex models that allow you to look into the future through time compression. What-if analysis may also be done by trying different variables. Disadvantages include the time to create and test the model. One common model is the Monte Carlo simulation, which uses random numbers to predict future outcomes. Additional key points on decision analysis. This is a decision-making process where we consider alternatives and their potential outcomes. States of nature are points in the process after the completion of a decision and are measured to assess the outcome of that decision. We create a decision tree to document and understand our options. We can deal with certain and uncertain outcomes. We consider our options and base our final decision on the outcomes. The maximax value is the best case result, while the maximin value shows when we will have the least risk. Finally, we consider using expected monetary value analysis to put some financials around each alternative to help us fine-tune our decision.